All right, all right, all right. QM, everyone. To kick things off, as always, our necessary disclaimer. The discussion today is not a solicitation for investment and is not financial advice. The Quill and corresponding wrapped Quill tokens discussed on this broadcast are utility tokens, and Quilibrium Inc. does not endorse or encourage engaging in speculation on the utility token of the network. There's also additional tokens that may come up in this discussion. The same disclaimer applies to those. Now, with that out of the way, we'll go ahead and talk about the mission as we do in every single broadcast. The mission is to secure every bit of traffic on the internet, whether it is in service of Quilibrium itself, in service of other crypto protocols, or the broader web. Cool. Okay. So let's go ahead and set the agenda for today. The stream's going to be a little bit amended from the original agenda posted on socials. So just to level set, the first thing we're going to talk about is, of course, news. We always do. The second part is going to be a BizDev update, and then items that are going to be coming up through this week, this upcoming week. If your week starts on a Sunday, then it's this week. If not, then Monday, whatever. And then we'll get on to the dev talk and a couple of other things I had left in store. So to start things off, first and foremost, 2.1, obviously it's in progress. The enrollment is in motion. It's had a bit of a hiccup. This is why we can't have nice things. The moment you put something online, people start to poke at it. We're getting issues with consensus around the frame progression. It's been an issue that we've been trying to tackle. We had a fix in place for one of the more painful points of getting that out, but it appears there is still one more thing that we need to tackle, and I'm going to describe that in detail during the dev talk specifically because it's going to update the state machine code, the consensus package, and a few other touch points. But broadly, we're getting it resolved, and we're going to be fixing this basically in a way that you don't have to upgrade right away to a 2.1.05. This will still work if you are on 2.1.04. You'll still be able to enroll, just keep your machine running, and it will pick up as soon as the frames appear. Okay, next up is BizDev. So we're working on the details of launch times for some of our partners. Obviously, with how this has gone, that has changed things for them as well with respect to when they're going to be doing their respective launch times, but we're still working out the details with some of them and also getting more teams on board as we are continuing to roll out our BizDev initiatives. There's also, just as a side update that's related to this topic, there's also going to be a bevy of mini apps that you've probably seen on Farcaster that will be joining us on Quorum Mobile for the mini app portion of Quorum Mobile. More in store on that, but that will probably be saved for the next broadcast. All right, so what remains this week? This week we're going to be going through the remaining launch items of 2.1. That's enrollment, shard out, then the unlock of all the primitives of the network, which we're going to be talking about during the dev talk portion, then the associated services, Q console, Q storage, Q KMS, the QName Service, and then Quorum Mobile and the bidirectional bridge. More details on these after the dev talk portion. All right, cool. Now that we got that out of the way, let's go ahead and jump into the dev talk portion. Like I said, just with the last broadcast, there's a lot we've had to cover, and also I'm on a really shitty laptop, so bear with me. It's going to be a bit of a inception moment as I try and move Streamlabs around. Okay, so for the dev talk portion, we're going to be diving into basically the meat and potatoes of how things run on Quilibrium. And for those who have listened to some of the prior broadcasts, this might feel a little bit repetitive, but the details are going to be where it's really crucial to pay attention to. To go ahead and start off, though, like I said, we're going to cover the consensus changes that are in place. So let me try and move some stuff around again. Okay, so if you recall from the previous broadcast, we talked about the state machine of the consensus engine being a very simple state machine. Well, a problem with being a simple state machine is simple state machines don't always handle complex situations like live networks, especially live networks with a lot of peers. At this point, we're almost at 800 peers. So what happens here is we need to get essentially that order of events. If you recall, we have the collecting phase, then the liveness check phase, then the voting phase, or actually no, the proving phase. And then finally the voting phase on top of that. And then finalizing and verifying. And it runs literally in this progressive order. It doesn't deviate except for if it detects an error during the steps between these phases. And if something goes wrong, then instead of going to the next step, it will turn around. Whoops. It'll turn around and, okay, this is just going to be another Excalidraw moment. Fun. It goes into this essentially parent phase called syncing, where we will resolve any issues associated with the data that it's holding that is causing it to hang up. And then it will move back to collecting. Otherwise, it goes from verifying straight to collecting. And that's it. That's a very simple state machine. That's what we've been testing for a long time, and things worked well in our test environments. But I believe the great warrior poet Mike Tyson once said that everybody thinks they got a plan until they get punched in the face, and that is exactly what happened for us. We had issues with the network as we rolled this out into the live environment, where there's a lot more unusual like setups for machines, sometimes people just outright being malicious, and just, you know, things happen. So what we're going to do is we're going to be breaking this out into a slightly more complex flow, and in some ways slightly simpler flow. The way that we're handling things now is kind of a like everyone tries to do the same thing, and if something gets in the way for one of them, it's okay because we have the redundancy of more nodes doing the same thing. And so if you're familiar with consensus algorithms, what we're amending this to is essentially in the family of consensus algorithms called hot stuff. Similarly, like I said before, our consensus algorithm itself, this simple portion, is technically just a Byzantine fault-tolerant consensus algorithm. And that means, of course, they're only able to tolerate up to 1/3 Byzantine failures. But the way that we actually augment this is that we have essentially a series of pluggable primitives that actually interface with the various phases that it's advancing through. And that's what gives us the additional hardness that enables the network to keep going in the advent of, you know, potentially greater than 1/3 Byzantine failures. And so the way that this basically works out is that the flow changes a little bit. We have the collection phase, which is instead of just receiving a new, basically a core of what the proposal is going to be, and I'm going to note these with a different shape so that you know what is a step versus what is data coming into it. Instead of it being just a simple collection, it's actually going to be a receiving point for what amounts to either what is called a quorum certificate or a timeout certificate. And the reason that this happens is because, like I said, in production, things can fail. In test environments, for some reason, you know, even when you're trying to simulate failures, things don't fail as bad. And so by consequence, we had to amend the flow. And so what the quorum certificate is essentially, if you remember the original shape from the protobufs that are on the repo as it is right now, there's a essentially a proposal. It is the portion that is essentially the signatures of all the members of the prover set that is in conjunction with the actual frame data. It gets coalesced together into a finalized frame and then gets broadcast as part of the network. But what we were missing is this notion of a timeout. Essentially, like nodes that are even honest, but for some reason there's something misbehaving about them. Either they are too resource bogged, or they're just, you know, hardware's going awry, or there's just something weird about it. It causes it to potentially pause. And if you have enough of these pauses, or the pauses are cascading in a certain pattern, it can lead to essentially it halting. And so the purpose of the timeout certificate is to basically say, hey, I noticed that in this period of time that was supposed to take X number of seconds, in our case 10 seconds, we didn't reach consensus. And so the purpose of the timeout certificate is to essentially jump through this and get votes on the timeout certificate instead of the quorum certificate. So basically what happens here is instead of it being just a collection phase for a new frame, it is also a collection phase for timeouts. And then when we get to the point of voting on it, we skip proving because there's nothing to prove other than the fact that the rest of the group of provers has agreed that we don't see anything and we need to see something. Then voting on that particular timeout certificate and producing it. And so what we're basically doing is creating two new wrapper types, the quorum certificate and timeout certificate, and the timeout certificate and quorum certificate have what is called rank. If you looked at the protobufs, you already saw extension methods on them from implementing the unique interface that exists. The purpose of that is to essentially give some simple pieces of data that the consensus engine knows how to work with, instead of having to rely on the raw protobufs that are coming through for the actual network-oriented stuff. The reason we did this is to separate consensus from the rest of the protocols so that other protocols could use our consensus. And so by consequence, rank was originally one-to-one with the frame number. The problem with doing that, of course, is if not everyone agrees that, for example, on the quorum, instead they're agreeing to time out while there's one or two nodes saying, hey, here's my proposal, guys, anyone? And there's nothing. How do you know which one to move to? So instead you separate it out. You put the rank and the frame number. The frame number is simply the portion of either the quorum certificate or the timeout certificate that's just advancement of state data relevant to what is more essentially a metadata about what the particular period of time in the network that they're talking about, whereas rank is just strictly a monotonically increasing number. So they're getting the consensus around that number instead of directly the frame number. And that's very helpful for us in being able to actually advance through this and know, if we had a quorum certificate or a timeout certificate and then we advance, we can distinguish which one of those came first. Because if you try to rely on a timestamp for that, that just leads to a whole another series of wonderful assumptions programmers make about time in which they will find themselves incredibly wrong. So instead, we just have a monotonically increasing number. Pretty simple. This changes the state flow a bit. Instead of having to basically work off this event-driven architecture where there are specific events, because in between each of these arrows is essentially a condition that says either I've timed out or I've received a given message or quantity of messages that allows me to move on to the next stage. Instead, it actually makes this quite a bit simpler. Instead of having a liveness check, the liveness check is essentially embedded into the heartbeat of the network, or as it's called in terms of the hot stuff consensus algorithm, the pacemaker. And so the pacemaker is essentially constantly keeping track of the liveness data. So that way we don't have to actually go through that part of the process ourselves. And here, oh, what in the world are you doing, Excalibur? Okay, so from here, we end up in this slightly augmented flow. We are still going to be doing finalizing, but finalizing and verifying. Well, actually, I'll put it this way: finalizing is part of this loop. Verifying is actually something that happens outside of the loop, and by consequence, again, it makes the flow simpler. And so, from each of these, we have a series of steps. Now, the proving part is where things get very unique from what we were doing. Like I said, in the existing consensus algorithm, we had this idea where all of the provers are going to be proving simultaneously. And this actually has the phenomenon, of course, as you would expect, since every piece of hardware that's running a node is different. The proof that it generates takes time, but the time that it takes is going to be unique to the machine. Some of the machines are apparently so slow at this that when they attempt to prove, they are somewhere out by 20 seconds. And the consequence of that is that this causes this staggered effect that accumulates very quickly, and then the network drops consensus. So instead of having that, there's actually essentially two different operations that the network can move into. And instead of these steps being actual steps, they are... Is there a way I can switch this? Nope. Damn. Okay. So instead of them being actual step operations, they are instead actions that they're taking that then produce outcomes. So for the one prover that is supposed to be proving, they will move into actually producing the proof. Everyone else will essentially move into a state where they receive any proposal. receive any proposals, and then proceed to vote on them based on whether or not they are valid. In addition, there's also some logic around receiving, duplicate votes if there's like bifurcated proofs, like if somebody's trying to equivocate, oh, that's still the same kind of convention that we already had. And then, of course, once the prover has proved, they're, of course, going to vote on themselves, goes into the voting step, and then finally we reach the finalizing step because we have reached either a quorum certificate or a timeout. So if in any of these steps we have a quorum certificate, like perhaps the network had temporarily forked and the other side of the fork already produced their QC, or we have produced a timeout certificate because the set of provers cannot determine the liveness of the actual prover that's supposed to be running, then these objects can get generated, and then they can choose to actually produce the vote outcome, aggregate their votes because we use a signature aggregation approach because that reduces the amount of data we actually have to communicate. And then we finally reach finalizing, which instead of it actually producing necessarily a new state, or at least a new frame, it is producing a decision, whether to advance the rank and reattempt the same frame because it timed out, or to advance the rank and proceed on the next frame because it succeeded. And that simple approach is essentially the way that Hot Stuff works. There's a few different tiny minutia about it, but I would recommend actually digging into the paper instead of trying to glean it from a simple Excalidraw drawing. It's just not going to be quite the same. The syncing step is also removed. The really cool thing that comes from this addendum is that we do add just a tiny bit more. I guess there's not going to be a way for me to do this, is there? Darn it. Okay. We do add a tiny bit more data inside the quorum certificate, which gives it enough information that it doesn't need to sync. The moment it receives either a QC or TC, it immediately catches up and doesn't need to do this syncing process. So it's just another benefit. We are actually, as weird as it sounds, given what I just described, we are actually simplifying the consensus algorithm by breaking it apart into smaller pieces. Okay. That's the big thing around consensus. That's what's coming out in the 2.105 update. That's what we're going to be getting the active prover nodes to move to, which will get anybody who is running 2.104 or 2.105 to immediately be able to enroll again. Now back to what we were talking about with the previous stream. So like I said, we have a bunch of different packages that are essentially the concrete implementations, because we have a bunch of interfaces that define the behaviors. So if you go into the, if I find the right folder, if you go into the types package, you'll see the various breakdown of types that we have, either for the Bedlam compiler, which does the garbled circuits. We have the channel types, which are related to our encrypted peer-to-peer messaging and group messaging, our cryptography-oriented types for raw primitives like signatures or VDF generation for frames, or KZG generation or KZG commitment and proof generation for the actual data proofs, verifiable encryption, and so on. Those are injectable interfaces that we use, so that way our tests are very easy to reason about without having to actually put in a bunch of concrete implementations. Because like I said last time, they're all implemented in Rust, and the moment you start doing native code interop with Golang, your test harness becomes so much more complicated to run. And we still have those tests. They are in our integration tests. So if you find a test that is appended in name with _integration_test.go for the file, then you know that it's actually going to be calling native code. But if it doesn't have that and it's just _test, you know you can run it even in your IDE. And so from there, these essentially get aggregated into our consensus engines, which will then call out into our execution engines when transactions process, which brings us to the meat of what we're going to be talking about in this stream. Specifically, our execution, the way that it works is very straightforward. We have essentially a parent manager harness for processing execution. It uses the information that is stored at the metadata vertex of a given app shard address to know what am I even executing? Like, am I responsible for tokens? Am I responsible for hypergraph entries? Am I responsible for multi-party computation, or is this at the global level and I'm responsible for, managing prover entries in the enrollment process? All of these break down into the same shape of an execution engine. And an execution manager is just simply the broker that uses the little bit of state that it knows to delegate accordingly. And so this is very simple. Like when we wire it into the global consensus engine, we wire all of the engines in. If we're on the app consensus engine, then we wire the relevant, usually 3, execution engines for the token, hypergraph, and compute primitives. If you're running one of the alt-fee basis app shards, then it's whatever the heck you've actually deployed. But that's something that's a bit out of scope for this. But basically, it's very simple. We wire it in, we initialize the engines, we start all of them. At the end, of course, it stops all of them. And when we need to perform operations, it will actually do what it needs to do in order to either calculate the cost of a transaction based on the current state of the network, calculate the cost is up there, but also determine which messages produce locks. So whenever we're writing state to the hypergraph, because this essentially, when you think about it in the context of, like graph algorithms, when you're processing a bunch of different shards simultaneously, there's cross dependencies between the shards if there's a transaction that touches multiple shards. And so we need the locks that come from it. I don't have this ordered in the best way. But there's the lock and unlock methods. There it is. Lock and unlock methods that essentially select the engine corresponding to the shard address, and then call the lock method to determine whatever the lock addresses are, and also induce the lock for the state of that frame so that we know for a fact that you can't have a conflicting transaction. This is what essentially prevents double spends. And then, of course, we have basic message validation. And of course, I already scrolled past it because the order is kind of weird, but process message, which actually takes the message, processes it, and performs any sort of materialization of state. So when you have a frame that comes through, obviously there's a consensus side, but on the verifier and receiving side, the frame comes in, has its bevy of messages that it needs to process. It will proceed to validate them, perform locks by processing them because it can be both in the same step. And then finally, it materializes the effective state changes that happen that are relevant to that shard. And so from that outcome, it ends up in essentially a pre-operative state that it has all of the locks that are in place, all the state changes that are in place, and they are in limbo until they get cross-shard confirmation for all of the various locks that needed to be processed. Confirming all of that, everything is good, it proceeds. So from there, yeah, that's everything on that one. From there, we actually break down into the individual execution engines. I'm going to go ahead and start with the global execution engine so that we can talk about what's happening with enrollment, and then we can dive into the 3 additional engines that unlock once we get into the post-initial enrollment phase. I'm also going to take this opportunity to see if there are any questions in chat because I, again, have a very janky streaming interface and I can't see everything all at once. Oh, good. I'm having this wonderful outcome of things lagging behind so I can't see. Cool. Let me check. How do I see the live chat? Well, I'm just going to put it this way. If you're watching on Twitter, that's fine. But if you're wanting to ask questions, I can't seem to see them. So I would recommend going over to Twitch to ask questions because I can't find them at all. Okay, cool. So let's go ahead and dive into the global execution engine. Obviously, this is the most relevant thing that is happening right now, given that is what we're processing messages for during this time. So like I said, there's a general slate of method calls that are every single execution engine has to implement: start, stop, validate, process, and then lock and unlock. And get cost. But for the case of global execution, like get cost is always 0 because it doesn't actually impact global state in terms of applicable size for impacting things like price, like how much the fee is for a execution. So basic premise, very simple. Every single message type that we have It is essentially an intrinsic operation. Intrinsic operations have a certain series of calls that they must implement, and in this case it's going to be a validate call, which is essentially self-validating for structural integrity. That is very important, because then the next thing that happens is we actually call into the execution engine's intrinsic for that given operation and then validate it from the intrinsic level. And what happens there is slightly different. We are actually taking the overall global state of the network and applying it to whatever proofs exist in the given message. For the case of global execution engine intrinsic operation calls, they're pretty simple. So you can kind of find a match here. Let me see if I can zoom in a little bit to make this easier. Okay. So we have, like I said, we have the engines and we have the intrinsics, and the intrinsics match up to the engine name, so it's not particularly complicated to go through. The engine has basically a single wiring through point that calls out to the operation, so it doesn't have to have a bunch of leaky abstractions to make it work. The global intrinsic is essentially what is kind of that glue. And it provides a couple of useful pieces of information, whether it's like generation of RDF schema, because like I've previously said, every single entry in the hypergraph of the network has a RDF schema that applies to it. That means that the network is essentially self-indexing and has semantic information about what is being stored, even if you can't necessarily read it. And so from this, we have like a few other details that are, again, intrinsic to every intrinsic. There's a sum check, which if there's any applicable sum checks, it performs them. If there is a derivable address based on the instance of the intrinsic, it will either derive it or have it cached and return it. In the case of global intrinsics, there's only one address that applies to global intrinsics, so it's just a static thing. There's the commit operation, which takes the applicable state changes that are happening when you're running process message and actually commits them to the local shard of the hypergraph, or in this case at the global level because it's a global intrinsic. There's deploy, which performs the deployment operation if the intrinsic is deployable. So like after this initial enrollment concludes, you can deploy things to the network. Whether that's a token or a like small shard of the hypergraph that you want to just have direct write and read access to, or if it's you know, compute applications, all of those things you deploy with the intrinsics deploy call. And that takes on whatever properties it needs to given the given intrinsic. Validate, which again, like I mentioned at the execution engine level, it calls that to validate the intrinsic operation based on the current state of the network. And oftentimes these are self-evident. So in other words, because of the nature of our proofs, like I talked about in the last stream, how our proofs are basically utilizing this roll-up strategy that commits to the global commitments of the global prover portion of the network. It takes very little data for these nodes to be aware of before they can adequately say, yes, this transaction's valid, because I already know that based on the proof that's been generated that this is a valid statement of fact, that I can move this data to turn into this data, add this, or remove this, or whatever. And then at the, like I said, at the validate level, we do have the individual operation validation. This is perhaps a little bit superfluous, but there is some degree of structural validation that happens here. It's a little bit convoluted as to why that's necessary, but just it's worth noting. And then we actually call the given operations verify method. So verify message at the execution engine level, verify at the intrinsic level, and then at the operation level verify to actually perform the operation level verification. And so we have all the different types that it's going to support based on whatever the intrinsic is. Sometimes there's a little bit of a crossover that happens based on the particular types of intrinsics that you're working with, but that's not too relevant to right now. And so that leads to the series of operations that exist, which is confirm, join, kick, leave, pause, reject, resume, update, and shard update. I'll get into what each of these do, but I just wanted to mention, like, you'll find a one-to-one mapping with these. And I followed a pattern of having the given name of the intrinsic itself followed by the operation name. And of course, underscore test or underscore fuzz test if a fuzz test, or underscore integration underscore test if it's a integration test. And then invoke step is the particular stepwise operation. Now, if you paid attention to the thing I just said about execution engines, you'd notice that it's not execute, or process. It is process message at the execution engine level, but it's invoke step at the intrinsic level. And the reason for that is because every single intrinsic supports this basically operation batching. For those who are like really deep in the weeds and listening to my progress updates on the social channels, you probably remember operation batching being something that really slowed us down a bit at one point. And essentially what this enables you to do is to do multi-step transactions that are useful for things like, I want to deploy something to the network, but it costs, Quill to do that, so I want to do the transaction that allows me to do that. And also I need to deploy this thing as well, so I can do 2 deployment steps plus the payment for both of them all in one step. There's of course an inherent limit to that, but this is very important for being able to do very quick operations on the network at a reasonable scale. Okay, so invoke step gets called by process message, and then if you recall what I said at the process message phase, there's the invocation, but there's also the materialize. So the operation itself is what contains the materialize step. That happens after it does the invocation itself. So it verifies, processes, and then materializes the given state change. Let's see. Let's start off with what everybody is trying to do right now, and that would be a join. The prover join is a pretty simple thing. It says what filters, or in other words, app shards that I'm wanting to prove on top of. So I'm going to be assigning my workers to these given filters, and it's going to be a request that was made at this given frame number. The reason why we put a frame number reference is because if you recall what I said in the previous stream, nodes hold 360 historic frames. Unless you're an archive node, then you hold all of it. And essentially that gives you some degree of malleability in the validity of a message. In the case of global intrinsics, that frame number validity is still within the 360. In the case of tokens, that can be all the way back to Genesis. And that depends based on the nature of when that token came to exist in the first place. Same thing with hypergraphs, same thing with compute. So we have the filter that applies to the given app shards that you're wanting to cover, the frame number that is the actual frame that you are trying to make the request at, not the frame number it gets included into, the requisite signature with proof of possession, and I'll get into that in a second, the merge targets, which I'll get into that in a second too, the delegate address in the case that your prover has a different address defined for rewards than your actual prover. This is really useful, like if you're doing a large series of node deployments and you don't want the spendable address, the key to that, to be on that given machine. And then the proof itself, which provides essentially the proof of availability and commitment of the workers. And I'll get into the structure of all of those in just a second. But again, get cost, materialize. Order's kind of wonky here because validate will be right after, I think. Nope, prove, then validate. Okay, go. So yeah, materialize, prove, get read and write addresses for locking purposes, verify, and I think that's it. Yeah, okay. So in the case of how these intrinsic operations work, essentially your node has the ability to prove any transaction as long as it has the requisite key material. You've also been able to see this in the documentation where you see the notion of a key ring. That key ring is essentially either a read or writable key ring that is, again, contingent on whether it's your node actually responsible for the proof or if it's just handling the proof on behalf of somebody else. And what that enables you to do is it enables you to either have a light node and do proofs or a active node and do proofs in the case of global intrinsics, because of course your node would need to actively manage key material in order to do a join. So let's get into the prove step. So when you are producing a prover join, you need the prover key. Prover key is essentially producing the signature that is important to demonstrate that you intended to make this transaction, just like any other, crypto network that exists. You use signatures to prove validity based on your attempted demonstration of what you're accessing. In this case, it is, I am trying to enroll as a prover for this given info. Merge targets, if you're familiar with the 1.4 to 2.0 era, we have this notion of seniority. It still applies. It's actually more relevant than ever. but seniority was something that is useful for when you're trying to disambiguate joins on the network. And I'll get to that in the confirmation step, but that's basically what it's there for. If you had existing keys, you can merge the seniority of them together non-additively in terms of like if they have the same applicable range, but if they had different ranges, then you can merge them. Then we have a signature that it produces over that, a signature that it produces over the join domain to actually confirm that you are intending to join. And this is probably the most important thing, even if it looks very like benign in the context of what's going on, the proof of possession. So signatures in this given curve that we use, which is BLS 48581, have this property called malleability. So when you're producing a proof, producing a signature, you have essentially a function that maps, your X being your private key times some sort of hash of the image of the message. And this produces some given output on a separate domain. So in the way that we handle things right now, BLS 48581 is a very large key size. Keys themselves are 585 bytes on the G2 point, and the G1 point is 74 bytes. So when we're trying to do, these signatures that are happening, and I might have butchered this. I don't remember off the top of my head exactly how it does the mapping itself algorithmically, but this is close enough to demonstrate the point. When you're producing the signature outputs, you need the signatures to be as small as possible because otherwise you're just going to be dealing with a lot of data that you don't need. So instead of doing like with some pairing curves where you can have equal sizes for G1 and G2, in our case, we use the G2 for the public key because it only comes up every once in a while versus the signatures, which will come up often. But here's the fun problem. Let's say I have 2 keys. And let's just say that this one is Y, and we will have some given message, and it produces a G1 point as well. And I'll just call this... we'll just call this YG1. It's not really important. It's just something that we can look at that helps explain what's going on. These elliptic curve points have a property that's, pretty much every single elliptic curve system has the same set of rules here. There's just some additional stuff involved with pairing-based curves. But there's this property that they are essentially additive, like they're linearly homomorphic, which means that you can produce some operations on the data without knowing the underlying data and the operation is still valid. In this case, the property that is homomorphic is the additive nature of that property. So when I give you the output signature on the G1 curve, you are getting a value that is a public point, and you don't know what the actual underlying secret key was because it requires solving the discrete logarithm problem in order to actually determine that. And until quantum computers actually work for once, we're not going to have to worry about that. And so in the meantime, while we're here in the real world, it is literally impossible for you to produce the requisite private key data from a given public point. And so what's cool about that, though, is that means that instead of having to verify, like normally when you do signature verification, like ECDSA, there's this series of steps that you have to do that kind of like smash the data around such that there's not a linear relationship between the private key and the output or the public key and the output. You have to do a series of different operations that are non-linearly homomorphic. And by consequence, that means that you can't do really cool stuff like this. So let's say I have 2 keys. And so that's XG1 and YG1, 2 signatures. And let's say I have 2 public keys, and I'll just call this XG2, even though that's not correct, and YG2. And if I wanted to validate the signatures on both of them, let's say they both signed the same thing. If I wanted to validate the signatures for both of them, then all I'd have to do is add these 2 values together, add the 2 signature points together, and instead of validating each one, like signature validation of a given message, a given domain, and I'll get to why that's important in a second, a given pub key, and a given signature, you can actually, instead of calling this twice, you can just add those two values together, keep the message domain the same, and run it, and it still validates. So that gives you this neat property called aggregation. And aggregation is really useful when you have a lot of provers that are actively working on the network. So for example, our network is going to be starting out with 4,096 literal shards instead of the logical shards that sit underneath them. And so by consequence, that means that you have to process 4,096 signature verifications times however many verifiers there actually are under those given shards. And that is just simply too much information for any any machine at any level to process and keep up with everything else it has to do. However, if you can just add those values together, then you end up with this fun property that you just validate that one single pub key point and that one single signature point, and you get the validation on that entire set of provers for one operation, much faster. There's also another step that lets you do this fun little mathematical transformation that will let you verify multiple signatures on different messages in the same domain all in one shot. I'm not going to get into that right now because that's too much of a rabbit hole and not important to the topic. The reason why I bring all this up is that the domain of the given message can be used as a form of attack. So let's say that I've created a public key that I don't actually hold the private key to. And instead, I am producing I'm just basically fudging a signature that is taking the value of a given target public key, and I'm just simply multiplying my data on top of it so that it looks like both parties have signed. And when you produce the output signature, it will be valid for both of those parties. And that is not what you want. So instead, what you can do is you can have a different signature that you require out of every prover joining the network that is unique to those signers, either because the message itself is unique or the domain is a different domain, or both in our case. And we use that as a proof of possession. So it basically mitigates this entire attack potential. The reason why we do this differently, like we don't have just a unique message, is the fact that this network has a lot of different signing operations that provers have to do. And in fact, if you have a prover, there might be times that you need to sign unique messages that aren't even part of the protocol. Like for example, for the QName service that I will be talking about later, if you're wanting to do an attestation that validates that you are a Q node operator, or you want to tie your node to that given Q domain that you have registered, you need the prover key in order to do that. But if the domain of the signature is the same for every single one of these operations, somebody could theoretically trick you into signing a message that would be sufficiently convincing to say that you are actually you're validating whatever that aggregate signature attack is for the underlying message. And so instead of that, we have a discrete domain that is directly controlled by what operation you're doing. And that domain separation, which you probably, if you were following the socials for a while, was a very big topic. That domain separation is what ensures the security between all the different operations, even when you're using the same key. And the node could not be misdirected into performing an invalid signature. Or a valid signature, but for the wrong purpose. Okay, long walk for a short drink of water. Let's get back to it. So we have this domain dedicated for proof of possession. And the goal here is to produce this public key signature, BLS 48581. We produce a public key entry, the signature itself, and then the proof of possession signature. The signature itself relates to the prover join message. The POP signature, of course, relates to just the prover. And it's just literally a signature on its own public key. And then under that domain, to be clear, that special POP domain. And then we get to the verification step, which will perform the act of verifying the data of the proof. It takes the actual underlying data of the proof. There is a additional step on the outside to essentially avoid Sybil attacks. So, somebody wants to spam the network with a bunch of joins. Like, how do you prevent somebody from just making a bunch of join messages if all they have to do is produce a signature? That's not very expensive. So we have this proof that you have to construct in order to join that is essentially demonstrating two things. One, you're holding on to data of the network at the global level, which provides at least a sufficient bar of confidence that you're actually, wanting to operate on the network as it stands, and you're not just broadcasting from God knows what. But more specifically, it is uniquely scoped to the number of provers that you have, their unique identifiers, and the aggregate filters that you are targeting. And so from that, we end up producing a special challenge vector that goes through that VDF proof, and then we verify that using a uniquely scoped VDF verification step that allows us to avoid having to process each VDF proof all in one shot, or all in iterative shots. They can all be done in one. It's kind of a similar thing that we do for KCG proofs. It's just a different algebraic domain. And then we also take the merge targets, validate the signatures of those, verify that the given merge targets haven't been used already, because if they've been used, then obviously we don't want people to just get free seniority. And then finally, we produce the checks on the output address of the prover. If the prover already exists at the global level, like, just simply the information about the prover, we don't write to that. But if they have already actively been proving and they are already joined in, we don't need to produce any more records. And if they're in a state where they've been, for example, kicked out due to malicious behavior, we're not going to let them back in. And then finally, we go into the individual checks against the given allocations that it needs to do. All of that, once it passes that, which is a lot of things that it says that I said that we're doing, but it's actually very quick to perform that validation. We then move into the materialize phase where we actually write those entries to the hypergraph. And that same thing happens on every single one of these, so I'm not going to dive into the validation and materialize steps again for any of them. Just the high-level notes, because that's a lot of info. So once you have produced a join for a given allocation, whether it's like a given set of shards, a single shard, or if you're dealing with like the global prover levels, there's that. Once you've produced that, you're in a state of essentially limbo. And that limbo is what we call an enrollment period. For the initial start of the network, we have man, I can never remember the number for this, and I always have to do the math every single time, so bear with me. So we have an 8,640 frame duration unique to the start of the network at 2.1 that essentially dictates that at this point in time, no one can confirm a join to the network. Normally, confirmations for joining the network as a prover is a duration of 360 frames. Why do we have this limitation? If you look at other networks like Ethereum or Solana, basically ones that have proof of stake oriented protocol behaviors, joining to be a prover is a commitment. And at the same time, being a part of the network is a commitment that can't just simply be easily withdrawn. If you do that, it would cause instability of the network. Like somebody could easily create a bunch of provers, say, yeah, I'm going to cover these shards, maybe participate for a few frames, and then just kill all their nodes and cause massive instability on the network. That would not be good. And so instead, what we have is this notion of enrollment windows and leaving windows. And it's the same process. It's 360 frames normally, except the initial enrollment window, 360 frames in which they have produced their intention to join or leave. And then after that 360 frame window, they can either confirm or reject their intentions. And what that enables us to do is to actually load balance the network more efficiently, because if there's this delay of about an hour's worth of time once the network is operating at a consistent 10-second clip, that gives you a degree of proof that says, hey, I know that this network, or I know that these nodes are coming into the network, these nodes are leaving the network, and that means that I know as a prover on the network, hey, there's going to be this ring 0 opportunity that is better than my current like ring 2 opportunity on the given shard I'm on. So I'm going to tell my prover to invoke its desire to leave at this given time for this shard, and then enter at this shard for this given time. And those line up such that after 360 frames, it confirms and leaves, or confirms the join and confirms the leave simultaneously and swaps shards. That lets the network load balance because it's entirely incentive driven. And so that's basically the purpose of this. And so the confirmation step is very simple. And it's literally just saying like, hey, I already have a join entry that's in this limbo of joining, or I have this leave entry that's in limbo of leaving, and I'm choosing to actually confirm that I'm doing that, which is why you'll see in the materialize step the type of status that we're operating in. If it's joining or leaving, it has a different series of steps that it applies to the overall state of that prover allocation. Pretty simple. Now let's talk about kicking. So like I said earlier, we have in our consensus model this notion of quorum certificates and timeout certificates, but that only helps us advance the state. It does nothing to indicate whether or not somebody is misbehaving. So let's say that you have a malicious prover, and I draw a little devil horns on it, but I'm really bad at Excalidraw diagrams, so I'll just tell you to pretend there's devil horns on this as a malicious prover. This malicious prover decided to actually generate two different proposals, and those proposals are sent to different sets of peers in the given click. If you were to have no ability of addressing that, then you could potentially fork the network and keep it consistently forked as a malicious prover, which could enable all sorts of problems. Instead, we have this notion of equivocation, which is if you are operating as a prover on the network, whether it's global or app shard level, if you equivocate, if you sign a frame that is for the same frame number, or a timeout certificate for the same rank as the quorum certificate, basically anything that equivocates, like saying, I agree to this and this. If that is detected, which it would be very easily because this is a mesh pub sub network, the moment that's detected, everybody else immediately votes you off the island. And so instead of actually doing a voting step for that, what that actually does is, again, because the network needs to stay stable, it essentially turns that prover into a, you're no longer actively allowed to prove, and you're only allowed to vote, and if you have any misbehaving votes, we'll kick you out immediately. But in the meantime, you just go into this like lightweight validation phase, and you're here until the duration of the network ends for you, which is like 360 frames. Your seniority has been slashed to 0, and once this is done, you're kicked out of the network for good. A node operating on the normal default client code that is published cannot equivocate. Equivocation is not something it can do. So the only way that you can actually enter this scenario is by misbehaving, and that's why we have the kick. And so the prover kick operation is literally essentially doing that. Like it's saying, here's who I'm kicking, here's the frame number that I'm making the request at, here's the conflicting frame 1 and 2, here's the commitment of the proof that I'm creating, the multi-proof prover for the public key and status fields that relate to that given prover that's being kicked, and then finally the traversal proof that proves that that prover was an active prover at the time of the kick. Because otherwise, of course, like you could cause all sorts of problems by just simply producing a bunch of shit that didn't even actually matter or was verifiable. So we have all these series of proofs that are required in order to produce a prover kick. And that's it. It just kicks. And so when you get to the materialize step, it literally is taking those entries and updating the status to left and also storing kicked frame information and obviously nulling out their seniority. Just like with join, we have leave. It lets you leave frames. Or lets you leave app shards. I'm not going to dive into the details of that. It's pretty obvious. Prover pause and prover resume. So these two operations are important when you're running a node and you need to do a long-term exit, like a, let's say I'm doing maintenance on my server and it's something that could take several hours. Normally, like if you restart a node, restarting a node for an update, for example, is very fast. It takes like less than 30 seconds on most machines to restart your node. So you actually won't even miss a interval of you being a prover, or at most one, and that's not really a big deal. Like the network handles that just fine. It's when you're not participating for a long period of time that is an issue. And so obviously this is the real world. People have machines that are based on real hardware, and real hardware can fail. So how do we support the maintenance of nodes that are operating? And that's where prover pause comes in. So when you are using a prover pause, you are essentially saying, hey, my node is still in the shard. I need to be offline for a little bit. I'm going to pause right now. I won't be earning anything for it, but I also won't get kicked out of my shard for not proving. And so that gives you a certain amount of time in which you can have your prover be a member of the network, not expected to produce any frames, not expected to handle anything. It is just simply there holding its slot before it gets started back up. Now, of course, there is a problem that like you could essentially abuse that. So if you had a prover pause, like you could use the prover pause in strategy with joins in order to, associate with multiple different shards that could potentially be a lucrative strategy by gaming the network. And so that's why the prover pause essentially has a limit. You are essentially stuck in this limbo for only a limited period of time before the network says, well, you paused too long, now you left. And so that's basically the premise of it. And then finally, reject. As I said earlier, the opposite of confirm. If you, for example, had a join and a leave because you were swapping shards, but others also entered that join and it put them in a higher ranking position than you because of their seniority levels, you obviously wouldn't want to accept it, so you would choose to reject your proposition. And then finally, prover update and prover shard update. Prover update is, sorry, one sec. Prover update is updating your prover information. If you need to change your delegate address, for example, like I have a prover that it needs to change what its payment address is because it's, like maybe it's been compromised or maybe I'm just rotating keys. It doesn't matter, lets you update it. Very simple operation, doesn't require a lot of work at all to process. And the prover shard updates are things that actually get emitted by the network itself. So it looks like an intrinsic operation, but it's not something that a normal node can actually just insert into the network. It's something that happens deterministically, and that is produced through the operation of the network itself. These prover shard updates are essentially updating your records for your rewards in order for you to earn on the network. I did mention that briefly in the previous broadcast, but this is essentially the operation that does that. Okay, now we are done with the global side. So that brings us to the three meat and potatoes of the intrinsics, which is the compute, hypergraph, and token intrinsic. I know a lot of you out there really care about tokens specifically, so I'm going to dive into that one first, and then we'll get into the other two. So on the token side of things, we have, of course, same entry point as the other ones. Token intrinsic, which is essentially, again, the entry point for any given token operation. But what's really important to notice about this token intrinsic is compared to the global intrinsic, at the beginning you saw that there was, this big preamble of RDF schema. But tokens are, many a beautiful and not so beautiful thing. And so they have different, behaviors that can exist on the network. And so in the token configuration file, you can actually see what those different configuration options are, and then also the validation methods thereof, and the production of RDF schema. We also have the hard-coded one for the Quil token, and lots and lots and lots of documentation about what these behaviors all amount to. And I'll briefly touch on them as we go through the intrinsic operations, but I just wanted to mention this is where all that metadata gets generated in order for the network to be able to index and, for your node to actually interact with those given tokens based on the information that should be stored for that given token's configuration. Okay, so let's get into the actual meat and potatoes of the token intrinsics. Let's start with the most basic one, transaction. So, like I said, we have these important cutoff timeframes. This is relevant to token intrinsic specifically because for the Quil token in particular, the way that the data was stored prior to the enrollment frame, that data is going to be very, very different on how we're actually producing proofs to interact with them. But high level, tokens have two major things. If you're familiar with UTXOs, this will be right at home for you. If you're not, what that essentially means is you have input values and you have output values. Unlike Bitcoin, these input values do not have an immediately public data. There's not something you can say oh, this address holds this amount of coin, and so I can spend divisions of that coin amount. Instead, we have commitments that we're working off of, which are not the actual values themselves. They are a commitment to the input balance. In other words, this is private information. We are utilizing the properties of the linear homomorphisms of elliptic curves in order to produce output transactions that still mathematically check out when you're doing sum checks and range checks on the values themselves, but the actual underlying data is not visible to anyone but the key holder. And to make that faster, we have some portions of information that get put into the private input values used when you're calling prove. They don't actually get materialized as part of transactions on the network. So proving this has obviously some variable behaviors, and this comes down to the type of coin you're dealing with. For example, the Quil token is a acceptable token. In other words, what that means is you can actually have a pending transaction that the other side has to accept or reject. And the reason why we do that is because it's kind of a fundamental flaw of a lot of chains where people can just send you a lot of crap you don't want. And what's worse is sometimes there's really serious implications of, holding those things, like on Ethereum, because they work off of an account balance model instead of a UTXO model specifically. It means that, like, if somebody, if North Korea sent you 1 ETH and, you had other tokens or at least other ETH in your balance already, your wallet's now been poisoned because you just had a, actively hostile and sanctioned nation state that has given you money, and there's no way to disambiguate your balance. And so the Quill token, supports proper compliance by having the notion of pending transactions, which means somebody can send you tokens, but you still have to accept them. It's not something that necessarily goes straight to your total account balance. Additionally, there's this notion of refunds. So in a pending transaction, when somebody's sending you a pending transaction, what that means is that they're saying, I'm sending X number of coins to you, and if you don't want to accept it, this is the refund address it'll go to. And on top of that, you can set an expiration date such that if the accepting address doesn't accept it by this time frame, they are no longer able to accept it, and it only is accessible by the refund address. This is really useful for solving a problem that exists in practically every network, which is I missent. Like, if you think about the number of people who have sent coins to the wrong address, hell, even in Quill 2.0, people were sending so many Quill tokens to the wrong address, and by consequence, they're cryptographically inaccessible. There's nothing you can do. It's essentially the same thing as burning them. And so, what do you do to solve that problem? Obviously, you can't solve it retroactively, but what you can do is you can change the way transactions work by introducing this refund structure. And this enables you to do a very easy exchange. Like, by having a refund address, by setting a time for it, you can very easily, like, say you're shopping online and you want to buy something that costs, like 500 Quill. And you are given an address that you can send it to. You send it to that address, except you send it to the wrong address. Like, you just mistyped something, or maybe they used some sort of integration to present the wallet transaction to you and it had the wrong address or whatever, but you sent it to the wrong place. If your refund address is just one of your other spendable addresses, then it doesn't matter, because you just wait out the time period before you can access your transaction and you get your money back. Pretty simple. And so that's why we have pending transactions. It's just solving a problem that's been long-standing and nobody ever bothered to fix it on their own chains, because they're just like, well, if you misspent, it's your fault. Consider it a donation to everyone. That worked back in the day when everyone was cypherpunks and understood the concept of proper key management, but that ain't the real world, and it's time to abandon that notion that the real world doesn't exist and we live in this cypherpunk future. We don't yet, and it's going to take a long time for us to get there. And so part of that means remembering the human. And so, yeah, that's basically the gist of it. We create these proofs based on the type of transaction that it is. In this case, it is a transaction, which means we have a existing pending transaction if it's an acceptable type of transaction, or if it is a non-acceptable type of token, then in which case it is just transaction to transaction to transaction, like any other UTXO-based chain. And so we do a series of operations with those linear homomorphic properties of the given curve that we're dealing with, which is decaf 488. I'm not going to dive into the details of that. I've done it way too many times already. And those properties are essentially what enables you to produce the output values such that the recipient of the coin can decrypt the data and know what they've received, whereas everybody else is blind to it. And that's what enables private transactions on the network. So there's also a few other properties. So like in a lot of networks have this weird thing where they have to specify the type of token. Like, for example, on Ethereum, if you have an ERC20, then it is something that is essentially treated as a fungible token. But if the units that you're dividing by is 1, technically, you could treat them as non-fungible tokens. And that's essentially what a non-fungible token does. It just essentially codifies the breakable units of that given token as 1, and that they are uniquely identified. Those two properties are essentially what dictates whether something is fungible or non-fungible. And rather than have to produce two entirely different transaction models, we can just leverage the same thing by setting divisible to 0. So if the, setting divisible to 0. So if the behavior of a token is not divisible, we treat it as a non-fungible token. And by consequence, that means that we expect that there's some additional data associated with it. That additional data is what uniquely identifies it, that non-fungible nature of that given token that's generated. And so that's straightforward. We just support it natively. The really cool thing about it is that we have this notion of the overall hypergraph of the network being this, massive like RDF-driven schema for the network that's intrinsically validatable and semantically accessible. And what that lets you do is, given whatever your token is, whether it's an NFT that corresponds to a image or a video or a in-game purchase item, like if you're on Fortnite, for example, and you buy a skin, V-Bucks can be the essentially the divisible token unit that you are using as part of your transactions, and you're trading them in exchange for the collectible items that are non-divisible and non-fungible, and those have corresponding address references that point to the underlying data stored on the network. And without having to actually rely on indexers, you can semantically determine that information because all of the metadata that exists for that item on the network is always present and available. So it's very, very unique in the sense that you can essentially tokenize anything on the network, and you can also understandably interpret that data without having to have some sort of external reference or rely on a third-party indexer or anything like that. Like, it's all just accessible to you at the time of your accessing of that basic information. That was a lot to go through. So like I said, we have the pending transaction that also corresponds to the pending output. So you're going from a token you've received and you're creating the pending transaction. This is essentially the other side of that, proving and validating over that, and then constructing the entries based on whether or not your token even supports it. If it's not an acceptable token, then this transaction will not work. It will fail every time. And then finally you get into the last part, which is minting. And this is probably where you will see the greatest wealth of creativity and all the different structures that will come out in terms of how tokens can be configured. Because this ranges from, minting with proof of meaningful work, which is how provers will get their coins minted out from actually participating in the network. There's mint with vertical proof, which essentially lets you produce a, like when people do airdrops and there's like a, preset number of addresses that have the right to do it. Well, you could produce like Merkle proofs like you do on Ethereum to lay claim to an airdrop. But if you have like, an absurd number of addresses that you're wanting to airdrop to, those proofs for those transactions get really big, and that's just too expensive. So instead, if you do a vertical proof, you only use 2 points, and it's 148 bytes of data versus the ungodly horror of however many sets of data that you'll need to do a Merkle proof. Even if it is logarithmic in growth. And then there's also mint with authority, which is your standard, I am minting these coins out to somebody. Mint with signature, which is essentially like a, two-phase exchange. Somebody gives you the signature that authorizes you to mint, but anyone can mint as long as they have that signature. Obviously, the signature is one-time use, but that's the trick. And then, of course, the biggest one that a lot of people will probably be taking advantage of, which is proof with mint of payment. In other words, being able to do payments in order to mint out directly. Now, that's curious, I imagine, for a lot of people, because while people who have dealt with like Monero or Zcash, they probably are familiar with whatever types of cryptographic tricks are required to balance the book, so to speak, for a given, for the given network token. And you have Zcash and Monero with their own token, and that's basically it. But when you get into another token, they have their own divisible units. They have, potentially varying costs. How do you balance that out? Well, it turns out actually it's not that hard. You can actually just leverage the same linear homomorphisms required to produce the necessary exchange for the sum check. So you just literally create that linear correlation in the production of the commitments when you're creating the prove with mint with payment, and it actually balances out. Like mathematically, you can actually just balance it out based on the divisible units. So it's very simple. And we actually have like the full description here if you care about the math side of that. And that's basically it for tokens. Let's go ahead and walk through the hypergraph portion and then the compute portion. And I think that'll basically wrap up our high-level walkthrough of Q. So let's talk about the hypergraph. If you remember from our previous streams, hypergraphs are literally like, you can think of a basic graph as a simple series of vertexes and edges such that, you know, an edge connects two vertices and that's it. Like there's obviously vertexes can be connected to multiple vertexes or vertices using multiple edges, but at the end of the day, all you get is one edge equals two vertex connections, and that's it. A hypergraph is essentially a multi-dimensional extension of a graph. It is a superset of a graph. And a hyperedge, instead of a regular edge, has this cool little property, depending on its construction. There's two different kinds that I'll talk about here. It's essentially this property that you can connect more than two vertices. Now, I mean, that alone is just kind of a cool mathematical thing, but what's really unique about it, depending on the construction, is that you can also, on top of embedding vertices, you can actually embed hyperedges themselves. And so you can have a hyperedge that refers to a hyperedge that refers to multiple vertices. And while you could say it's turtles all the way down, the unique property of that multidimensionality means that you can actually represent any relational data structure that exists, whether it's a, you know, obviously since it's a superset of a graph, of course it can contain a graph. But when you get to things like relational databases, you can actually express a relational database using a hypergraph. And RDF, the semantic schema that we use for the network, can be expressed with a hypergraph. And so those two properties, when you like start to let them melt together in your head, you can actually realize a really convenient system for using the semantic data of the network to automatically serve as an indexed database, thinking from the perspective of relational databases, to query anything about the network, provided you have the keys. And that's essentially what our hypergraph enables you to do. And so that really cool property comes out in a really simple way. When you are creating a hypergraph, like you're deploying it, you need to define the structure of your data. And if you don't follow the structure of your data, obviously the transaction will reject. But the gist of it is very simple. So when we get to, I'm just going to search for it because, man, my organization is not the best thing in the world, but I mean, bear with me. I wrote 6 million lines of code here. I'm going to have to forgive myself a little bit on the ordering of function names. But essentially you have this notion of deployments which dictate the, at least at start, the shape of the data that you're able to deploy. And so that metadata is at a standard place on every single shard on the network, so there's no craziness that you have to figure out in order to find the given metadata of any of the intrinsics. But that metadata includes the RDF schema, which has to validate. If it doesn't validate, it doesn't deploy. And also the schema includes all of the underlying text, so if you add comments or something, that's fine. But do note that if you do add comments or whatever, it's also going to count in terms of cost because it does obviously impact state size. And so from that leads to all of our operations. In particular, the vertexes are what cares the most about the RDF validation. And so when we are creating the data on the network, we'll proceed to validate it. And this operation happens under verify. When that data is being stored on the network, because this is a hypergraph, and because our hypergraph, like I mentioned in the previous stream, is a CRDT, it's actually really simple. We just create a vertex add, and that's it. Once it's been validated, all we care about is storing the network data. So we have the encrypted vertex data itself that's verifiably encrypted. So it's using the MVC and the head proof that validates that the encryption was done correctly. And then we actually store it. What that actually allows you to do is some really cool things with data sharing. So say, for example, you create a hypergraph shard that you want other people to send you data about. Say, for example, let's say I am a researcher and I want to get data from a bunch of different sources these people don't trust each other with having the other side's data, but they trust me with being a broker of it, or alternatively, they trust each other with being a broker of it when they both agree to the data. And so essentially you have a read key and a write key. The read key is used to validate that the data was written correctly, that it is valid for that shard. The write key is what authorizes you to write that data. So if both parties have the write key, but not the read key, they can't read each other's data. But if they use a compute primitive for key generation that is mutually generated, they can actually mutually construct a key that allows you to decrypt the data together if both parties agree. And in the meantime, that data being written, is valid even if you don't have access to anything but the public key, because the proof is an MPC in the head proof that essentially demonstrates the Lagrange interpolation of points is sufficient to construct that data that is produced as the statement. The witness values being, encrypted values that essentially create that construction. And so that's a really powerful primitive that lets you do data sharing without actually revealing the data, such that you can mutually compute over that data for whatever purpose. So the researcher, for example, can have both parties sending over their data about, like maybe it's like a patient study from two different pharmaceutical companies, and they can't give that data to each other, but they can mutually share it such that they're constructing a set together that produces a output value that doesn't reveal anything about the original inputs, but is sufficient to, tell you something happened. Like if two, I don't know if this is going to get flagged or not if I say this. So two certain type of vaccine manufacturers collaborate and put their data together about patient outcomes and what, whether or not there's a correlation to things that could happen as a consequence of that. The researchers could have, like, without seeing the patient information, they could get their outcome result. Like, is it significant or is it not significant statistically? So that's why the hypergraph's a very powerful tool, and it's why it's its own intrinsic, because there are going to be times in which data sharing, file sharing, whatever, needs that degree of control and that degree of semantic interpretation that lets you have, like, queryability. And then finally we get into compute. Oh, I guess I should mention real quick, the vertex operations, if you didn't hear it last time, vertex add, vertex remove, hyperedge add, hyperedge remove. Finally, the compute intrinsic. And so on the compute intrinsic, we have, again, same process. There's deploy, there's verify, there's the lock operations, there's materialize. The purpose of the compute intrinsic is actually, it makes it sound like you're going to be doing the compute right here in the intrinsic, but it's actually a out-of-step operation. It is something that simply schedules the compute to be done, such that the provers that are actively working on that shard will establish a onion-routed channel for you to communicate with and actually do the requisite compute. And that produces the proof output, which then gets serialized as part of the intrinsic code finalize step. So this is actually going to look really simple compared to some of the other intrinsics in terms of what it's doing. It's literally just like breaking things down into an execution DAG for multiple operations. And then the execute step is just incrementing through that DAG. And then the finalize is producing the finalized outputs in terms of hypergraph entries, if relevant. That's it. The actual magic happens inside of Ferret, which is our oblivious transfer library. As you can see, we have it's a pretty simple interface, although I did add a note there. If you remember earlier this year, we were having issues with multi-threaded interactions on Ferret, so I actually put a hard limit of single-threaded access to do Ferret for now until we figure out what the root cause of that is. It's not accessible by code normally. You'd have to manually edit it to cause this to happen, but I guess it's worth noting since it showed up. Anyway, the purpose of Ferret is to actually do the multi-party computation, which provides, again, compute over private inputs to a shared value that both parties can see. And that's basically the gist of it. I think that pretty much covers it for now. I didn't realize I was going to have a nearly hour-and-a-half marathon run, but here we go. All right, so let's finally get into the last part, which is, I guess, what a lot of people were waiting for. So there were two things that I was originally going to cover. The first was going to be covering QConsole and associated services. That's going to be delayed because we're still dealing with the rollout of enrollment. So that is tabled for now. But what I will talk about right now, and this is, what there's some cool stuff to talk about, is the QName service. So the QName service, this is what will be going live with once the enrollment process completes. This is where people will be able to claim their Q identities, whether they're doing it as a username or a Q domain. The truth is, behind the scenes, these are actually the same thing. Like if you're claiming a username or you're claiming a domain, they are the same thing. It's just the for the end user, when they are creating an identity, they may have certain attributes that they want. Like they may want people to publicly access a username, but they may not necessarily want to have routing information for a domain unless it's privately given, or vice versa. There can be any sort of behaviors that will matter based on the use case, but at the underlying layer stored on the network, on the hypergraph, these are actually the same thing. But we have that distinction because it makes it easier for users to go through the user registration process. And so maybe a few things you noticed if you're looking really closely. So I'm not going to dive into all the, oh, great. I made it so that it resizes itself. Crap. Okay, let's try this again. Okay. So I'm not going to dive into all the details yet, but the process is very straightforward. You try to register a username. Obviously, that username's already taken, so I can't register that. But if I was trying to snipe blah blah blah's username or yogurt boy's username while they're available, this gives you the option to register usernames or domains. There's a pricing tier, but what's very unique between ENS versus QNS is that it's one time. There's no repeat registration. And you can see all the values are denominated in Quill. And obviously this is on a test net, so I'm not actually stealing anybody's name right now, but you get the one-time price output on it, obviously 3 characters or less. The denomination breaks down based on the size of the name. And when you continue to payment, you will have your options available based on whether or not you want to use USDC or wrapped Quill or native Quill, and then you'll be able to proceed to payment. And again, for those who are paying attention, there are some other things of note here. And when you do this, you will go through the process, and then you will actually do the transaction. What's really important, I guess, and this is kind of one of the big surprises I wanted to talk about, was the fact that by participating in QNS and buying Q names, you will also gain access to governance points, which are essentially tokenized entries that are related to governance of the QName Service protocol. Because at the end of the day, QName Service being operated by a single company would be absurd. Doing that would be absurd. And so as we move on with the QName Service, it needs to become something that is governed mutually by users of the service. Because there's going to be times where there's going to be hey, somebody took this trademarked name, and we need to have an arbitration over this because this is leading to a lawsuit. And so we need some sort of governance system in place for that. And what better than the actual users of the protocol? So by participating in buying QNS names, you acquire QNS points, which will essentially serve as governance points. And I guess the one last thing I wanted to mention real quick. Like I said, there's about 800 nodes that are currently live on the network, and I took a snapshot of those. And the reason I took a snapshot is because, one, thank you for running nodes even this early when we're having these issues as we're trying to get through the enrollment process. Obviously, I don't want you to feel like your time has been wasted, and so by consequence, you will also be granted access to free registrations for Q names on QNS, which will of course have associated governance points as well. And so those are the two big things that I wanted to mention at the end for those who were curious about what the one more thing was. And there's many more surprises to come as we go along. Alongside that, you can kind of see that same flow that exists in Quorum Mobile. When you get into the profile section, you obviously can see whether or not you have a premium username associated with. That's a QNS name. And when you go to the premium section, you can see the available usernames, If you already have one, it'll also give you a few riffs on existing ones, and of course denominated in Quill, and you can search for it and so on. But the other side of that, I guess I'm actually on the wrong thing here. The other side of that is that these badges, as they show up here, these are actually attestations, and those attestations are surfaced through the QName service. So together, collectively, like the QName service is doing way more than just names. It's also doing like all this annotations and attributions that are, privately disclosable. Like you're choosing whether or not to show this information to others, but it can be used for any types of attestations. So you can like do a tripartite attestation using a zero knowledge proof of like a passport, for example. So if somebody wanted to set up an attribute or an attribution that says, hey, like I'm making this this space on Quorum, like it's only for people who are living in France or something. I feel like there's somebody out there that resonates with. And so you can actually use a zero knowledge proof from someone's passport, because the passports in Europe at least, but most countries have a near field communication. And you can actually use that NFC signed statement to produce a zero knowledge proof that certifies that the government of France has authorized your passport without revealing any information about yourself, just the annotation that you're from France. And that is privately disclosable. You can choose to disclose to other people that you are a French citizen, and therefore you have the right to enter that space, but give no additional information about your personal info, like no name, no address, just citizen of France. And so that's like the really powerful composability of the features of QName Service, the attestations, the overall marketplace that emerges for these names. Like all of these things feed into each other and kind of turn into like this massive flywheel of what information you're actually wanting to let others know about, and what way you wish to present your identity on the web. All of that, unlike the existing infrastructure of the web, which is all about monitoring and categorizing and selling your information to the lowest bidder, is just like completely inverted. You are choosing to give information to certain people such that they're the only recipient of it, and no one else can see any of it or know that you even gave it to anybody at all. That's the central like power of Q. So with that, I think it's a pretty good time to go ahead and close out for the evening. Thank you all for watching, especially for those who were based in Europe, because I know that it's very, very, very early there. So we'll go ahead and wrap things up. I'm going to take a brief moment to look at the chat feeds, because again, I have such a hard problem trying to actually get these chat feeds. I don't know why, it just like lags or something. But once we have, I guess I won't say that yet, but we'll be streaming somewhere else soon. Okay. I don't see any additional questions. If you do have any questions and I missed it because this entire like streaming setup is just kind of bonkers, feel free to reach out. Like I've said before, I'm on all the socials. You can find me. I'm also on Farcaster at Cassie. I'm on Twitch, OX Cassie. I'm on Twitter as Cass on Mars with underscores in between each. Or you can catch me at Quilibrium Inc. on Twitter, but that's actually more than just me, so do note that like that's not just me you're talking to. So, like I said, thank you all for watching, and I will see you all next Sunday.